Hey folks, Todd Coburn here with your Aerospace Structure series. This video is on NASTRAN, focusing specifically on how CSHEAR panels are used. Let's take a look. So first let's look at this lecture assumes you already have some knowledge of NASTRAN and you're ready to move on to shear panels. If you don't, be sure to go back and watch the rest of my videos on NASTRAN here on YouTube. So this is a look at the CSHEAR card as defined by NASTRAN. We're going to have the CSHEAR command, an element ID, a property ID, and then the 4 grid points around the edges. Now it's important to understand the order of the pick, because that will determine the orientation of the CSHEAR panel. So we're going to get our x-axis going from G1, the first grid point, to the second. The y is going to be perpendicular acting toward the G4 direction. This is the definition of that, what all those inputs are. Pretty straightforward for this particular card. Now, while this was the CSHEAR orientation on the left, on the right here, we see how CSHEAR forces are determined. So, in contrast, thinking back to what we know about CQuad 4 elements, CQuad 4 elements are membrane elements, where we are getting running loads in all the component directions and running shears. We can also get transverse bending capability and some other specialized effects. Shear panels, on the other hand, are a shear-only element. So, they don't have axial load capability, they have shear capability. However, to temper that statement a little bit, they also have the ability to, in this process of modeling our shear behavior, they develop kick forces. So there's two things. Part of it is intuitive, the other part is not intuitive. So we're going to have a shear flow in the panel. That's the shear that it's carried, written as a shear flow, pounds per inch. And we also, since that shear flow results in a running load along any surrounding members, what that means is that shear flow, anytime the shear flow is non-zero, it's going to change the forces, the axial forces in surrounding members. Going from one to the other, it's going to change that axial load from one value to another value. And the way NASTRAN models this is by introducing corner forces. The corner forces here are shown, and they're numbered by the grid point that they're at and the grid point where the force is coming from. So as you can see at grid point 1, we have two forces. We have the force at node 1 coming from 4, that's F14, and we have the force at node 1 coming from node 2, that's F12. So, and you'll notice at each of the other corners, you're going to get corner forces where they're defined by the grid point number. The first indice is the grid point number that it's at, the force is at, and the second indice is the grid point from which it's acting, and they're going to be aligned along that directed line segment. So that's how those corner forces are defined. Now what this means is our shear flow is introducing a change in axial load in adjacent elements, and the way NASTRAN deals with that is it reports these corner forces as well as the shear flow. Now the corner forces are introduced, they're defined as being positive, acting in that directed line segment direction, which means they're always pulling away from the element. If they're positive, they're pulling away. This means they're never going to be both positive, because that would mean they're pulling against each other. Not possible, because the shear flow is acting one direction, so both of these are going to represent that flow going in the same direction. The two will be going in the same direction. So that's kind of our orientation. Now you're gonna probably just barely starting to understand that, or you might feel like you understand it, but then when you start trying to use it, it'll get cloudy again. So stay tuned and we'll try and make all this clear for you. So once again, this is our NASTRAN orientation. This is the way NASTRAN forces are defined. And we also are going to need a property card. So the property card for a shear element is the P-shear card. It's got the name, it's got the property ID, the material ID, a thickness value, and two parameters, F1 and F2. Now what happens is, those of you that have been doing structures for a while are aware of the idea of effective skin. When we have skin, a lot of times the skin, you know, if we have like in a fuselage, we have stringers, they have axial area, and the skin also has area. But a lot of times the skin is in compression. If the skin is in compression, buckling can cause less of the skin to be effective than the full width of skin. And so we define an effective width of skin around each stiffener based on the number of fasteners and how they're laid out and things like this. We define an effective width of skin that we lump in with the stringer to give a better analysis. This is commonly done with compression. Actually, shear lag can also cause us to use less than effective skins for for structures in tension and such. If you understand this idea of effective width of skin, then you're probably going to be tickled with the C-shear element, because where a C-quad element is fully effective, all of the skin is giving axial area for any C-quad, and the only way to adjust that is to model your effective thickness as being different, which changes all the capabilities of that element. A C-shear element, you can define how much effective skin is acting with the edges, with the corner members, the edge axial members. And the way it does this is with this F parameter. You're going to get two F parameters, one for the two parallel edges, and another for the other two parallel edges. Let's look at the property card to get that laid out better. Here's the property card, and here's where that F1 and F2 are defined. That F1 is going to be the 1 to 2 line and the 3 to 4 line, and F1 is going to control how that effective width is handled, and F2 will handle how the other two perpendicular edges are handled. And the way it does this is we can specify that F parameter to be 0, which means no effective skin, which means that element, that shear element, works just as a shear element, and it doesn't add any area into the surrounding members. If we set F1 and F2 and or F1 to be larger than 1, actually larger than 1.01, what we're going to end up doing is getting like an effective width of skin. Like a common rule of thumb is 30T, and if you set that to 30, that won't give you 30T of effective width of skin, which means half of 30T for each panel, since a edge stiffener will have only half of the effective width from that one panel and half from whatever panel is on the other side. So that's the way it models it. Any value, if you put F1 or F2 larger than 1.01, then you're going to get that much effective skin. So if we put in a value of 30, we're going to get 30T of effective skin. If we put in 20, we're going to get 20T of effective skin, and so on. Now, if that F parameter is less than 1, what it does is make that like a percentage, if it's less than or equal to 1. So if F1 and F2 are 1.0, that means you have 100% effective width of skin, and it's going to actually use the area of half of the width of the panel in the same manner that a C-quad would. But if you set that F1 parameter to, say, 0.5, that's going to give you 50% effective width. 0.2, 20% effective width. So once again, we can use these F parameters to either set some multiple of the thickness as our effective width, or to set some percentage of the width to an effective width, or to set no effective width. And reading this will tell you how that's done like we just described. We're actually going to see this in play in our examples today. So stay tuned. You don't need to bog yourself in the words too much at this point. Just stay with me, and then you can come back here for reference later. So once again, to re-summarize, if F, and I'm using this Fi because there's F1 and F2. Usually we will assign the same number to both F1 and F2. That's simpler and straightforward. But this allows you, let's say we have a floor beam, so Two parallel edges represent the caps, and you may want 30T effective width of skin, and the other two parameters represent the stiffeners, and you might want a different number for effective width of skin. And this allows you to model that, okay? So Fi means F1 or F2. If there's 0, there's no effective skin. If it's smaller than or equal to 1, it's a percentage of the panel width in that direction. And if your F1 is greater than 1.01, then it's a multiple of the skin thickness, like 30T, 20T, 15T, whatever. If you need a refresher on how to calculate effective width of skin, you can see my Aerospace Strength Handbook, Volume 2, Section 10, and that will tell you how that's done. Brune also goes into great depth on this and some other references. Got that? So let's dive a little deeper into what these forces mean, because that is actually the hardest part of the CSHEAR element, is understanding how to use the forces. It's actually a very simple element, but it doesn't do everything that's intuitive, and also it kind of hides some of its results. Once again, this is a refresher on what our CSHEAR orientation is and how the forces are aligned. So let's go ahead and look at what these forces on the element really mean. While this picture is in all NASTRAN manuals of the way the element is defined and the way the corner forces act, let's look at how this actually works. And we'll do it on a rectangular element, which is a little easier to understand. This is the actual exploded free body diagram of what is really happening when you have a CSHEAR element. So first of all, we have the panel itself. It goes G1, G2, G3, G4. And on that panel, we have a shear flow, Q. And while I'm showing Q2 and Q3 and Q4 and so on the different edges, these shear flows are going to be the same. A positive shear flow is going to be acting in this direction, in the standard positive direction, where we've got positive up in the Y direction on the positive X face, and positive X direction on the positive Y face, negative Y direction on the negative X face, negative X direction on the negative Y face. Okay, so looking at that panel, that's positive shear flow. If you get a result that's negative, it's going the opposite direction. Next, you have to recognize there are 4 imaginary rods surrounding this element. No matter whether or not your model has rods or bars or some other element along the panel, anytime you use a CSHEAR element, you're going to get 4 imaginary rods surrounding the panel. Each and every CSHEAR panel. Now, when you think about what we know about action-reaction pairs, you realize, well, if we look at the G23 edge, we have a shear flow acting up on the panel. And if that is the correct direction for the shear flow, we're going to get a corresponding equal and opposite shear flow acting on the adjacent rod in the other direction. And it's going to be acting on this imaginary rod that the CSHEAR element introduces. We also have corner forces. If you look at that imaginary rod, the corner forces that are applied to that by NASTRAN, as we see in the CSHEAR forces, are going to always be acting pulling away from the rod for a positive direction. On the lower edge, we've got F at 1 coming from 2, F at 2 coming from 1. At 2, we also have F2 coming from 3. We're missing the 3 subscript. F3 coming from 2. F3 coming from 4. See that? So each rod has not only those corner forces, but also the corresponding shear flow in the equal and opposite direction. This is going to end up giving us equilibrium on all of the members. Now, you're going to see these shear flows in your output. You're going to see these corner forces in your output. But it's not going to end up in the elements you think they're going to end up with. This is the only place it'll be shown, and you're going to have to deal with that separately. We'll see how that works in a moment. So this is how it's done. And if you're only barely starting to grasp this, or if you're a little bit skeptical, stick with me, because all will be clear after we run a few examples here. So let's go ahead and look at the output before we look at some examples. This is the output coming out of NASTRAN for every CSHEAR element. You'll notice you'll notice there's an element ID over here to the left. We have 4 points, point 1, 2, 3, 4, and there's a lot of data and it's arranged kind of in a haphazard manner. So the force from 4 and the force from 2 at node 1, those are your corner forces. Your shear flow is the shear 1 to 2 value, which is identified here and shown here. So force from 4 at node 1. So this would be F1 from 4, which is this value. F at 1 from node 2 is this value. The kick load in this panel is 0, and this can account for out-of-plane forces, and we'll deal with that in a separate video, since many times that kick load is going to be 0. And our shear flow here is between point 1 and point 2. That's why it's kind of offset here. And that's shown right down here as 100 in this particular case. So we've got 500 pounds. We've got 2,000 pounds. And we've got 100 pounds per inch. Now at node 2, that's a fancy way of writing 0 coming from 1. We have 0 coming from 3, and we have a shear flow of 100 pounds per inch, and so on, okay? This is how you map those. So let's just take a look at mapping all these values. If you're having trouble tracking with me reading off of here, then go back to our definition. Remember, we had that simple definition coming out of any NASTRAN manual, which just shows the shear flow and those corner forces. This is the way it actually works. You draw the panel, draw the surrounding elements, the imaginary rod elements, and then draw your forces. And we're going to do this step by step, so stick with me. So let's go ahead and map these forces coming from a typical output to this diagram here. Once again, this is what you want to do is start by drawing your elements. So draw a little square panel, and it doesn't have to be this big, it can be small. Identify your 4 grid points, and then draw 4 rod elements around it. Remember, regardless of whether you have rods or not around it, NASTRAN is going to generate what could be considered imaginary rods surrounding that panel. So draw them with hidden lines like this to show that they're actually not shown in the model, but they're there, okay? So we've drawn this. Now we're ready to start mapping our forces. First, what we can do is map our shear flow. You can look at this and see, well, let's see, from 1 to 2, that's from here to here. And we can see from 1 to 2, we have a 100 pound per inch shear flow. You see that? Now remember our positive. This is from 1 to 2, but actually our positive is shown here to the left. Positive is acting up on a positive X face in the positive Y direction. And so if you go node 1, node 2, node 3, this is going to be positive up. And then all the other directions will be corresponding. Remember, shear forces and shear flows are romantic little guys. So this upward force is going to be greeted mouth to mouth with a sideward force. And then we're going to be greeted, so these little romantic forces are mouth to mouth and toe to toe. So down below, since this one's going this direction, this is going to have its toes intertwined with the vertical force. And this one's going to be mouth to mouth and toe to here up at corner force. You can see we've got grid point 1, mouth to mouth, grid point 3, mouth to mouth, grid point 2 and 4 are toe to toe. So since our shear flow is defined as being positive, that defines the shear flow on the right face is up, the left face is down, the bottom face is left, and the upper face is right, as shown. Now you notice all we did was draw those shear flows acting on the element in the positive direction. That's the first thing. And we identify not just the direction, but the magnitude. They're all 100. Sometimes we'll just write 100 right in the middle of the panel to show that they're all 100 pounds per inch. But a lot of times it's convenient and more clear to write it right there in the corner between the two flows. Since these two mouth-to-mouth flows have to have the same value at this corner, these two toe-to-toe ones have to have the same value, and so on. You can draw it just like this. Now, once you've drawn your positive shear flows, or whatever the corresponding direction, in this case they're positive, on your shear element, now you need to remember action and reaction pairs. So now for this vertical shear flow acting from G1 to G2, we have an equal and opposite shear flow acting on that imaginary rod. For our actual shear force, shear flow acting on G4 to G3, we have an equal and opposite shear flow acting on the imaginary rod. At the left end, and the reaction pair. At the bottom, the reaction pair. We now have dealt with all of our shear flows. We're ready to start moving on to plotting our corner forces. So next we're going to look here at our first corner force at point 1. We've got this 500 pounds acting from grid point 4. That's going to go right down here at node 1 from 4. Now, while it's at 1, it's convenient to show that it's acting on this imaginary rod right on there. So this rod experiences this upward shear flow acting on it, and also experiences downward force acting at grid point 1, acting on that imaginary rod. Next, our next force is at 1 coming from 2, and that's going to be going this direction right here. That's 2,000 pounds. Now we're going to at 3 coming from 1, which was 0, at 2 coming from 1, and at 2 coming from 3. Then we have at 3 coming from 2, at 3 coming from 4, at 4 coming from 3, and at 4 coming from 1. Now, let's look at these a little further. Notice our first one, this 500. Let me back up a little bit here. This 500 is positive. That doesn't mean up. That means it's pulling away. If we go back to our definition of the forces, positive corner forces pull away from the panel. This is positive. If we go to our next one, our second one coming from node 2 is also positive. That's pulling away. At node 3, that's essentially 0. I'm going to show that as pulling away. And 0, which I'm going to show as pulling away. Then we have 1,000 positive. So it's pulling away. And then we have 0. Where do we go? Let's see. We're at 3 coming from 4, which is right here. It's 0. It's weird the way these are aligned. The kick force is down here. This is your F from 4. And then we've got at node 4, we've got minus 2,000. So remember, positive is acting away, so minus is acting towards. And at grid point 4 coming from 1, positive would be pulling away and negative would be pulling toward. Now, if you look at this, we now have a complete free body diagram. If you look at your panel itself, you'll notice it's perfectly balanced, as all shear flows are, because this force times this distance is equal to this force times this distance. It's perfectly balanced. There's no moment. All the forces are balanced. That shear flow acting on this edge equals the shear flow acting on that edge, and so on. Perfectly balanced. Now, if we look at our rods, let's look at starting with the bottom rod. We see on the right end at node 2, we have no axial force in that imaginary rod. But then what we have is a shear flow acting 100. Now, this panel is actually 20 inches long. So 100 times 20 ends up with, by the time we get to the end, we have 2,000 pounds. The shear flow is pulled such that we have 2,000 pounds of tension in the rod by the time we get to the left end. It's going from 0 to 2,000 through the mechanism, the shear flow that's acting on the rod. Now, if we look at the vertical rod on the right, we had a 0 on the bottom, and yet we have a shear flow of 100 times the distance, which is actually 10. So 1,000 pounds accrues by the time we get to the top. So the bottom rod is going from 0 at the right to 2,000 pounds. The cap is, that imaginary cap. The right vertical stiffener is going from 1,000 pounds to 0. The upper cap is going from 0 to 2,000 pounds of compression. And the leftmost rod, which in this particular case was the reactionary wall, has a 500 pounds, 500 pounds. So it's 500, and then it's reduced by 100 times 10, which gives you, which ends up, and you end up with another 500. Those are your two reactions, 500 and 500, and that's introduced, that 1,000 pounds of total force is introduced by that 100 pounds per inch acting on the 10 inches. So you notice that all imaginary rod elements are perfectly balanced. The shear element is perfectly balanced. Everything is perfectly balanced. The problem is the forces here don't show up in your model. They have to be taken from here. Now, if there's no rod elements along the edges, you may remember to go and grab the rod forces out of the shear panel. But if there are rod elements around it, it's very easy to overlook these forces that are being induced into those imaginary rods, which must be superimposed on the surrounding rods. Now, you may not be convinced and you may not completely understand, but stick with me, and this will be clear after a few examples. We're going to do a few examples with no surrounding rod elements, just whatever C-shears develop, and then we'll do a couple with surrounding rod elements. And by the time we're done, you should understand how this works. Stick with me. Oh, and this is how our stresses are defined. Our stresses is, in this particular case, we have a stress of 1,000 psi acting on the panel. It also gives us an average shear stress, which is the same value. And if we define a shear allowable in your material card, then it will write a margin of safety, and it's going to output 2 elements per line of output. In this case, we only have 1 element. So that's how it works in that shear flow. That shear stress is just Q over T as always. Okay, so let's start looking at some examples. That's the basic building blocks that we're going to need to understand shear usage of C-shear elements. Our first example is a simple cantilever beam. In fact, all of our examples in this particular lecture are going to be cantilever beams to keep it simple. We're going to fix both left end nodes. These are the properties and the applied loads. If we wanted to model this with C-shears, we would do that like this, where we're going to have the typical case control and executive decks, where we're defining our constraint cards and our load cards, and also what output we want to dump to the FO6. We create our grid points here, and this is a 20-inch by a 10-inch panel. We now write our C-shear, which is going to be CSHEAR element 1 using P-shear property ID 1, and it's going to be numbered from 1, 2, 3, 4. Our P-shear card is property ID 1 using material card ID 1. It has a thickness of 0.1, and we're going to start off with full effective widths, where we just define 1 for our F1 and our F2. And then we have our material card, our typical constraints, and our applied load. You got all that? So this is the piece that corresponds with our shear element. And since our F's are equal to 1, we're going to get a percentage of skin. And since it's 1.0, that's 100% of the skin. Not 1%, 100%. Okay? 0.01 would be 1%. All right. Now, before we run this model, we should actually predict what's going to happen. These are pretty simple calculations. We can see that our reactions will just be M over that height, which is defined as W here. So 2,000 pounds in and out of the page, pulling away down the bottom node and pushing toward on the upper node. Our vertical forces is just that force, and half of it could be expected to go out each constraint. So 500 pounds acting in the downward direction. Our caps, we're going to need the cap area to get our properties. And since we're using full effective width and there are no surrounding rod elements, it's just that 10 inches times 0.1, which is the total area of the panel, and half on the top and half on the bottom. So we're going to use that would be a ½ inch. From that cap area, you can now calculate what the effective moment of inertia is, and that is going to be about 25 inches to the 4th. It looks like our number slid off. The lower cap is equal to negative the upper cap stress, which is MC over I, 4,000 psi. Our shear flow is just that force divided by the distance, which is 100 pounds per inch. Our shear stress is just the shear flow over the thickness, 1,000 psi. Since we weren't given G, we were only giving our E and our Poisson's ratio, we can calculate the effective G. We now can calculate our shear deflection, which is just the shear strain times the perpendicular length, which can just be written as the shear stress over G times that length. Looks like 0.0052. And our bending deflection due to the axial properties of the web, PL cubed over 3EI, typical formula. And the total deflection, vertical deflection, would be about 0.0159. So these are our predictions. This is what we're looking for to compare our output to what should have happened for this really simple model here. So let's go ahead and run this in NASTRAN, and once we do, let's echo our predictions here to the screen. This is what we're going to get. This is extracts from the F06 file. We're going to get our first and last nodes are fixed. You'll notice we have a little deflection in the axial direction at node 2 and 3, as you would expect, because actually the thing can move a little bit. But what we're really focused on is the vertical deflection. Now you notice those two vertical deflections are a little different based on where the force is applied, but we see that the greatest deflection occurs at node 3, 1.345 inches, 0.01345 inches. We can see that our forces at the constraints are 2,000 pounds, just as expected. And we also have vertical forces of 500 pounds, as expected, and in the expected directions. And then we can see the shear panel output and the shear stresses. We can see the shear stresses are correct by inspection. We're going to actually drill down on the shear forces a little further in just a minute. But this is showing about 15% error for the deflection, which is not bad given the assumptions that we're making here. Okay, so that's basically how we can create and run a shear model. Before we plot out those forces further, we will be doing that shortly. Let's go ahead and look at another example. This particular model, we're going to now use and idealize the skin is only being 30 T of effective width. Remember last time we assumed full effective width, the whole web, which means half the web in each imaginary cap. Now we're going to stick only 30 times the thickness of width in each. To do that, we make our model like this. You'll notice this model is identical, except for this card here. You'll know the two F parameters are 30. Since they're greater than 1.01, that means that NASTRAN is going to calculate the effective width of skin, the area, based on whatever we put in there is a multiple of the skin thickness. Okay? So let's do our predictions here. Most of these are going to be the same, like our reactions will be calculated identically. Our cap areas are now different. It's this F1, that percentage, 30, times the thickness, so 30 times T, and then that's going to be times the width, and then times the thickness is the total area. And we're going to put half of it in each cap. So that's how we do that. Now we can calculate our moment of inertia based on that cap area, which is 7.5. The last one was 25. Now we're 7.5, way less for the effective width. This is our cap. Our lower cap is going to be in tension, our upper cap in compression, MC over I. We have a much different prediction for stress based on the quite different areas we're using. Shear flow is unchanged, shear stress is unchanged, G is unchanged, shear deflection is unchanged, but our bending deflection based on our moment of inertia is now less, which means we would expect a lot more deflection. Okay, now our results, if we look at those, we're going to recall our model and our predictions. This is what we get, and you'll notice we're about 13% error. So once again, we're around a 13-ish% error, no big deal. So we can either model this with full effective widths in this case, or with partial effective widths like 30T. Let's go ahead and run another case. Let's assume 10% effective width. Now if we wanted to do that, our model will look the same, except now we would put in 0.1. Since as we see here, Since our F parameter is less than or equal to 1, we're still using an effective width, percentage of panel width. Remember in the first example we did this, we made this 1.0, and that gave us 100% of panel width as our effective area. But now we're only assuming 10% effective, which means that since our F1 is less than 1, that's 10% effective width, and that's going to result in some different calculations. Our reactions are the same. Our cap areas are now different. It's that percentage or factor times our width times our thickness, and half of it's put in each cap. That means we have a much smaller moment of inertia, which changes our stress, doesn't change our shear stresses, changes our axial stress, and it also changes our bending deflection for a total deflection of 0.1119 now. We're getting more and more deflection because we're modeling less and less area. So these are actually quite different models. One of them, we have a panel where we expect all of the width to be effective, like if we have a really thick panel. Second model, we use 30T effective width, like when we have compression on one of them, we don't expect a lot of the panel width to be able to work with the caps. Except there were no caps except for what we modeled. This third one is assuming 10%, which means we're almost completely ignoring the skin for axial load carrying capability. This is our results here. Once again, we repeated our predictions, and we can see we're about 22% error. We're a little higher error with this particular idealization, but it still works, still can be used. All right, let's look at another example. Now let's go to 1% effective width, but this time we're going to use rods around the panel. Our first three examples had a shear panel with no rods. Of course, since it's a C-shear element, NASTRAN assumes rods and creates forces on those rods that we need to account for. In fact, it needs those to act like a cantilever beam. It's critical to that model running. And we would have to evaluate those rods. But now we're actually going to model rods. This is a more common modeling scenario where we have a C-shear element, we have members around them, rods or bars or whatever, and we want to understand, we want to keep that panel either being just a shear element or being a shear element with only a little bit of its thickness adding to the area of the surrounding members. If we were to assume 1% effective width, along with those actual CROD elements, this is how we'd model it. Let's take a look. Once again, we have the exact same model, except this assumption of how much skin is effective and what we're going to put in our rod. Now, in this particular case, we're going to simulate our first example, which had a ½ areas. It had a ½ area because we basically assumed that the shear panel had fully effective width, so we basically dumped all this area of the web up at the cap, okay? In this case, now we're going to have a rod with that area plus a little bit of skin. So let's take a look at how this model should look. Here's our model. You'll notice this part has to do with the idealization that's unique to the other examples. We have our shear panel. We have our P-shear card, which is saying we want 1% effective width, so it's 0.01, so it's a 1% effective width of skin. We also have rods around the panel. We're not putting a rod on this left end because we actually have a fixed constraint there. It's like there's a wall, so we don't actually need a rod there. So we only have rods on the bottom, top, and right ends. And we're going to give those rods area such that we have the same area as we did in example 1. Now remember, this model is using 1% effective width of skin, which comes out to be 0.005 inches squared of area. That leaves, if we want to model that first example, which had a ½ inch of area in the caps, we will model the area of the caps of each C-rod with 0.495, as you see here on the P-rod card. So notice we made this area 0.495, and since we're using 1% effective width, that's going to add 0.005 inches squared of area, which means the total area of the cap, when you count for both the rod and the imaginary rod, you're going to have a ½ inch area, same as we had in example 1. That means our prediction should be identical to what we had in prediction 1. In example 1, as you see here, you'll notice all these numbers are the same. as example 1 because we have the same CSHEAR panel. We have the same caps. Now we did it differently because in this case, we now modeled those rods with C-rods and we augmented them with just a little bit of P-shear effective width. But the cumulative effect of the C panels area and the rod area is the same total area as our original model, 0.5 inches squared. Hence, same predictions. Let's look at our results. So this is our structure and loading. This was the predictions we just had. These are our results. If we look at our deflection, we have almost identically the same deflection as we did in example 1, about 14-ish% error. You'll notice our forces of single point constraints are correct. Now, we get to the rod forces and we're going to expect, wait a minute, our rod forces look wrong. And our rod stresses look wrong. The rod stresses should be 4,000 psi, but we see here they're only about 2,000 psi. So something is grossly wrong. Well, these C-rod forces, while it is true that those C-rods have this much force in it, what's also true is the shear panel added force into those rods, and it doesn't show here. It shows down here underneath the C-shear panel. So our rod forces and our rod stresses are wrong. They have to be augmented if we want to get a correct result. Stay tuned and we will unravel this mess. So we're going to stick with the same model, and now what we're going to do, recalling what the structure looks like and what our predictions were and what our output said, let's go ahead and draw the forces on our element. Remember, this is our nomenclature. This is how all the positive values are determined. And just like we did earlier, we can now draw the panel, draw the imaginary rods, and now in addition to those imaginary rods, we also need to draw the actual rod. See that? So we have our panel, we have our imaginary rod, we have all the corresponding positive forces shown. We also have a real rod, which is superimposed on the imaginary rod. I've drawn them separately so we can see them, which also has force. Now, if we map the forces from our output into our nomenclature, we're going to get this. Notice we have our panel with its shear flow, and it also is acting on all the imaginary rods around it. If we plot all these forces from node to node, as we did before, we're going to get these forces on the imaginary rods. We then go over here and take our axial forces. Rod 1 has 2,000 pounds of, let's see, those are stresses. Here's our, where's our rod forces? Here we go. Rod 1 had 990 pounds of tension at node 1 and node 3, right? That rod has just, it always has a constant force. Rod 2 has 490 pounds of tension. Rod 3 has 990 pounds of compression. Now, if you look at this, we find out this is correct. If we start with a shear panel, this is completely balanced, right? As we saw before. Now let's look at this lower rod. This lower rod is not two separate rods. We don't have a C rod and an imaginary shear rod. We have a single rod, and it's idealized with these two pieces. So the total force at the left end is 990 plus 1010, 2,000 pounds, perfectly matches our prediction. And when you divide by the area of a ½ inch, you find out we have the 4,000 psi as predicted. At the right end of the rod, we have the C rod, which is 990, and the shear panel imaginary rod, which is minus 990. The sum of those is 0. Down here at node 2, coming from 3, we see those two also oppose, and we end up with a net force of 0. Up at the top, we have 510 in the imaginary rod and 490 in the real rod, which means we have a total of 1,000 pounds. Remember, we had 1,000 pounds applied upward, and this perfectly matches. The way the load gets into the structure is 1,000 pounds are applied. It runs down that rod. It shears out into the panel, and the zero forces of the upper and lower cap get changed into more and more compression on the top and more tension on the bottom based on the shear flow, as we see here. At the left end of this rod, we have 90-90 plus 10-10 of compression, resulting in 2,000 pounds of compression, as predicted. Along the left end, we end up with 1,000 pounds of force being applied into the wall, which actually feeds that imaginary rod, which feeds our reactions. Everything is balanced, and now we've accounted for everything. Now, the careless finite element modeler will run this model, look at their rod stresses, conclude that the axial stresses in those surrounding rods is 2,000 psi, and they will be 100% wrong. Only half of the stress. 2,000 psi is not very much, but if this were a real loading, that could easily exceed allowables. It's critical that when we have shear panels, we have to account for the effect that those shear panels have on the surrounding rods, and we need to superimpose the rod forces for any surrounding members on the CSHEAR imaginary rod forces when we evaluate those stresses and forces. So you can see that this is perfectly balanced. We said that, and this, we said this, I believe. Got those ideas? All right. I think we've got one more example. Let's go ahead and take a look at the exact same model, but this time, instead of, remember last time we assumed 1% effective width of skin, let's go ahead and assume no effective width of skin. This keeps it even easier. Let's just stick the area we want in the C-rods. So that means if we want to keep matching example 1, we'll take a 1/2 inch of area, stick it in the C-rod, and don't account for any imaginary effective width of skin from the panels. In fact, the way to do this is you could say, well, if I want effective width of skin, I will just calculate how much that is and add it to the actual C-rod area rather than letting NASTRAN control that effective width of skin with its shear panel effect. Now, this does not eliminate the need to account for those imaginary C-shear rods, as we're going to see. But it does keep our inputs even simpler. Let's take a look at how it looks. Our model is going to look identical, except for our Fs. If you look here, you notice that under the C-shear panel, we now have made F1 and F2 equal to 0. That means no effective width of skin, 0. Okay? We still have our rods, same way we did before, but now we're giving them a full 1/2 inch area, which will perfectly model, it'll perfectly match what we did with no C-rods in example 1, and what we did with example 4, where we had a C-rod that had most of the area and 1% of the area came from the effective width of skins. Okay? So once again, we have no effective width of skin, so all the cap areas can be placed in the C-rods. Our predictions now will match example 1 perfectly. As you see here, no difference at all. So the predictions for example 1, example 4, and example 5 are the same. But the way those loads are carried, or where the areas are coming from, may be slightly different. Okay? So let's go ahead and look at our output. Here's our model, here's our predictions, and this is our results. We can see we have about 14% error here, which matches what we saw for example 4 and for example 1. So actually, there's not really an analytical benefit to doing it this way. This just may make it simpler and easier to keep track of for you to model Fs with 0 and put all the raw area you want in the C-rods themselves. We can actually use any of these approaches, modeling with some 30T of skin, modeling with 1% skin, modeling with full effective width of skin, modeling with no effective skin. We can use these with identical results as long as our idealization holds. Usually there's going to be some effective width of skin. We often won't want to ignore that, But whether we put that in the rods themselves, or we model them in the CSHEAR elements, or we model part of it in one place, part of it the other place, can result in nearly identical results, essentially identical results. Okay? You'll notice here, if we look at our single point constraint forces, they're correct, but our forces in the rods are still wrong. Just because we put in 0 in our F, it did change how we introduced our area into the rods, but it did not fix the problem that the C rods are being reported now with only part of the forces, because we have to include those imaginary rods that surround the shear panel in our rod forces. So to take this to the next step, let's draw this out. There's our results again. That's our nomenclature. And this is how that looks. Now you'll notice we have because we put 0 effective width of skin, we have nice round numbers in the coming from the shear panel, at least for this example. Once again, you have to superimpose them. So at node 1 coming from 3, we have 2,000 pounds. At node 2 coming from 1, we have 0 pounds. At node 2 coming from 3, we have 0. At node 3 coming from 2, we have 1,000 pounds upwards. At node 3 coming from 4, we have no force at all. And at 4 coming from 3, we have 2,000 pounds. That's how you debug this. These forces agree perfectly with predictions. These are the forces that we need to write our stresses on when we're evaluating our model. This example underscores the need to post-process our results to superimpose the forces in the imaginary CSHEAR rods on any axial forces of any axial members going this around the panel. Okay? Said this. Let's go ahead and summarize what we've learned here. This is our model of how we're putting those together. Our recurrent idea is that anytime we have C-shears, the shear flow in those C-shear elements is going to change the axial force in the surrounding elements. And that needs to be accounted for. Okay? We're going to actually say that a few different ways here. Our C-shear elements are going to allow us to control how much effective width the skin adds into the surrounding rods and bars. We can model with whatever we think makes sense. How much effective width? 30T is a common number. Our C-shear elements can be used without surrounding elements in many models, as long as the F1 and F2 are not 0. If these are 0, you're going to have surrounding members to pick up those loads. However, best practice is going to put rods around any C-shear element. Also, in my opinion, best practice may be to set those F1 and F2 to 0 and just to add whatever effective width of skin into the rods in the actual rod area rather than letting NASTRAN do it. But anyway, either way works. Axial forces in our surrounding rods and bars has to be modified to include any corner force effects from any adjacent shear panels. We've said that a few times. Now, thinking back to what we know about CROD elements, and those have area that's proportionate to the thickness, C-shears give us a new capability because we can have an axial stiffness that's not got anything to do with the thickness. It can be based on panel dimensions or some effective width of skin, something like that. Those are the benefits of shear panels. The greatest risk with using C-shear elements is to forget to account for the forces that they induce and to superimpose them on the axial forces of surrounding members. So let's go ahead and take a look at some examples of usage quickly. We've seen before some different ways to model frames with C-bar elements, with C-shear, with C-quad elements and rods, or C-shear elements and rods. All of these methods have been used successfully by folks in industry for decades. And while it is trendy to overcomplicate the model and to make a lot of fine detail in simple models that would otherwise be simple, I believe the best approach for many large-scale structural models is a simple representation coarse model that accounts for the stiffnesses you need and some post-processing to support that. Some other examples. We talked before in earlier lectures about this modeling study. This was a modeling study I did a bunch of years ago. This is showing frames modeled with bars. This is showing frames modeled with a 2-rod single shear panel model. And this is showing a frame model with 3 rods, a quad, and a shear panel. This particular study was run back with in the early 90s. And I did these kind of studies both with McDonnell Douglas's CASD program and also with NASTRAN. This is that nose model I created back around the same period of time. Now, in this case, since the nose of an aircraft is pressure critical, so usually we're assuming full effective lifts for most of the skin. So these shell elements were all quad elements, but these floor elements use shear elements. This was actually a CASD model, but oh, excuse me, this is a NASTRAN model. I'd actually done this with CASD as well, but this is actually a NASTRAN model where we're using quad elements for the fuselage skin and shear elements for those floor panels. So that is a quick look at how to model with C-shear elements. In the future, we're going to have some more videos and more content in my book covering other examples of usage of both quad elements and shear elements and how those can be used effectively. But for now, hopefully you've got enough to chew on and to make sure that you don't fall into one of those easy to fall into mistakes with using shear elements. Enjoy.